All right. I hate technology.
Interesting.
Apparently not enough. And I need to write more of the code. I just don't want to. Coding is traumatizing. But I just that to you. So anyway, now where we were was last section 7.5, given as second order linear homogeneous ODE of this form, how to obtain a solution using Homogeneous method. Some cases you can find both linearly independent solutions. Probably saw the example last time Bessel equation. Some cases you only use Homogeneous method to find one solution, and we still need to find the other. So I'm going to establish a theory about these kind of ODEs to see how to proceed and find that second solution. So first, we talked about linear operators before, and here we have an example of linear operator, a linear differential operator that's applied to y. And what that linear differential operator does is take derivatives of y, multiply them by functions of x, and add them up. So then this ODE can be described in this very compact form. Operator applied to y equals 0. And that makes it a lot easier to establish certain things about the behavior of solutions to be able to work this more concise form of an ODE. You may have seen in your first differential equations class theorem for existence uniqueness of solutions for a first order ODE. It's simply called the existence uniqueness theorem. And we do have a similar result for second order ODE, which makes sense because a second order ODE can always be written as a system of first order ODEs. So here's the theorem. That if we have an ODE in this form, now this one's not homogeneous. We can have a function capital F of x on the right side if you like. And then two initial conditions because it's second order. That if the functions involved, p, q, and f, are continuous on some interval containing the initial point x naught, then we know that this problem has a unique solution on that interval, and the solution has two continuous derivatives. So we're at least assured of having a solution under really mild assumptions on the problem data, just continuity is enough. Now, suppose we have two solutions of the homogeneous form of this ODE. The differential operator applied to y equals 0. So we'll call a solution y1 and y2. So here we have y1 being a solution, y2 being a solution. And now you find y to be a linear combination of those two solutions. C1 and C2 have to be constants. So then I can see if this y is a solution. And because the differential operator L is linear, and differentiation in general is linear, I can write this out. If I gather all the terms involving C1, I get this part, and then gather all the terms involving C2, and I get this part. But then I get, so Ly is equal to C1 Ly1 plus C2 Ly2. But y1 and y2 are both solutions of the ODE Ly equals 0. So the whole thing is 0. So this is something that's true of linear differential equations in general, that you have, linear homogeneous equations, I have to emphasize that. If you have two solutions, any linear combination of them is also a solution. And what I've just done is establish this theorem here. Yeah, any linear combinations of a linear homogeneous ODE is a solution. Here I've shown it for second order, but it applies in higher order as well. So, if any function of this form is a solution, is it true that any solution is a function of its form? And that seems like a very difficult question to answer, but really to establish that all solutions are of this form, it's enough to show that any initial conditions possible can be satisfied using a solution of this form. So here I have this linear combination of y1 and y2. And I want to see if I can satisfy any initial conditions whatsoever. So I have my two arbitrary initial conditions. The y of x naught is y naught, my prime of x naught is z naught. And I try to enforce these initial conditions on this solution here. And that's going to give me a system of two linear equations in the two unknowns, C1 and C2. Now I can write this system of equations in matrix vector form. So I have this matrix that has y1 and y2 up top, y1 prime, y2 prime down below, all evaluated at x naught. A vector of unknown coefficients C1 and C2. And then right hand side U naught has my initial values. And as you've heard me say before, mathematics is a problem reducing all problems to linear algebra, and that's certainly true here. We want to know if this system can be solved for any y naught or z naught that we have. And the answer is yes, if this matrix has a non-zero determinant. That's what it guarantees, that that this system of equations has a unique solution for any right-hand side values, y naught and z naught. Well, what is the determinant? Nice and easy for a 2 by 2. So it's y1, y2 prime minus y2, y1 prime. And we want that to be non-zero. And that determinant is called Wronskian of y1 and y2. Now, I'm doing all this for second order ODEs. If we had a higher order ODE, like an ODE of order m, we would have m initial conditions. You'd have m constants defined. Your system of equations would be m by m. Your matrix would have like y1, y2, the ym up top, and then y prime in the second row, y double prime in the third row, and so on. And that system would have to have non-zero determinants. So you define Wronskian appropriately in that case. Wronskian is always the determinant of the matrix of the system that you use to satisfy whatever initial conditions you have. So, if Wronskian is non-zero, we can satisfy any initial conditions. So we're able to characterize all solutions. So that gives us this theorem. So if you have two solutions for your homogeneous second order linear ODE, and if a Wronskian of those two solutions is non-zero at a given point x naught, then it's always possible to find constants C1 and C2 that y satisfies the ODE and y satisfies any initial conditions. Furthermore, it's actually another statement I can make. constants that we get, very unique. Any questions up to this point? Okay. And we also have this theorem that that if you have any two solutions where Vronsky is non-zero at a certain point, then every solution can be written in this form. That's why we call this solution the general solution, because it describes all possible solutions. Whatever constant C1 and C2 you need, satisfying whatever initial condition you have. We also say that Y1 and Y2 form what's called a fundamental set of solutions of this ODE. So all it means is you just have to find two linearly independent solutions, and you got everything. So as an example, here's a second order linear ODE with constant coefficients. And using techniques that you would have learned in your first course on ODEs, you would find two linearly independent solutions. The y1 is either minus 2x, y2 is x e to the minus 2x. And if you were to compute for Wronskian, so here's y1 and y2. So we have y1, y2 prime minus y2, y1 prime. So we go ahead and work all that out using the product rule in this case. And this is what you end up with, e to the minus 4x. But as an exponential, it's never 0. So that tells us that y1 and y2 are fundamental solutions by the previous theorem. That you can express all solutions of this ODE in this form. With one of the homework problems, you're actually showing that the Wronskian of y1 and y2 being non-zero is equivalent to showing that y1 and y2 are not scalar multiples of each other. That is, they're linearly dependent. So, so that's one way to look at it. That when you're checking Wronskians on zero, you're checking if y1 and y2 are linearly dependent. If they are linearly dependent, then they will describe all possible solutions.
On my other student, we weren't shown necessarily this side of it, but we use I call it the W matrix.
Yeah.
To check if it was.
Okay, yeah. So yeah, and actually I think I do cover that when I teach that class also. So yeah, that's how you show that you have your basis. Okay. Now, and I can see in the flashback here with these kind of ODEs, that how do you go about solving something like this when the coefficients P and Q are constant? You're solving this quadratic equation to get to roots lambda 1 and lambda 2. And if the roots are real and distinct, that's your general solution. You have these two exponentials. The Wronskian would be non-zero. In fact, this is the Wronskian right here of e to the lambda 1x and e to the lambda 2x. What you end up with is this product of these exponentials. These are never 0. And if lambda 1 and lambda 2 are distinct, then this is non-zero also. So you're guaranteed a non-zero Wronskian. So in that case, everything works out beautifully. That e to the lambda 1x and e to the lambda 2x form a fundamental set of solutions. And this is your general solution. But that's in the case where the roots are distinct. What if they're not? Because if I had lambda 1 equal lambda 2, if you go through this whole process, these exponentials would be the same. This would be 0, so the Wronskian as a whole would be 0. So I'd only have one solution as opposed to two linearly independent solutions. Now, in your first DE class, you would have learned how to get a second solution, and I imagine some of you could rattle off what that is, and actually, it did appear in a previous example. But my goal here is to show that in general, when you have only one solution and you need a second one, how are you going to get it? Even for ODEs that do not have constant coefficients. Okay. Now, it turns out that there is a formula for the Wronskian of any fundamental set of solutions of this equation, even if y1 and y2 themselves are unknown. So let's suppose you have two solutions. So you have these equations from them. And then what I do is I multiply the first equation by y2 and the second equation by y1 and subtract them. Well, the terms involving q are going to cancel. And this is what's left. Now, at first you might be thinking, well, so what? But if I take the derivative of the Wronskian, because the Wronskian of y1 and y2 is a function of x. So I fill in what the Wronskian is, y1, y2 prime minus y2, y1 prime. If I work out what this is, using a product rule, you see that these terms in the middle cancel. And we're left with this, which is exactly what you have here. So, in other words, we have a derivative of a Wronskian plus p of x times the Wronskian is 0. So the Wronskian satisfies a relatively simple first order ODE. It's relatively simple because it is separable and it is linear. That's like the nicest kind. I can just write down what the solution is. It's an arbitrary constant times its exponential of the antiderivative of minus capital P. And this is called Adele's theorem. That if you have this ODE where P coefficients P and QX are continuous on some interval, for whatever solutions y1 and y2, the Wronskian is of this form, a constant times this exponential. And Wronskian is either never 0 or always 0. It depends on this constant c. It really boils down to Wronskian non-zero or they're 0, depending on whether the two functions y1 and y2 are linearly dependent or not, or they're scalar multiples of one another. But the nice thing is that we don't even know what y1 and y2 are. This is still a Wronskian. I read Adele's theorem. Okay. Now, Whereas the second order ODE, you can only have at most two linearly independent solutions. To show you that, I'm going to assume that three solutions exist, y1, y2, y3. Now go ahead and compute the Wronskian. The Wronskian of three functions is this determinant, where you have your three solutions in the first row, first derivatives in the second row, second derivatives in the third row. So this is how Wronskian generalizes to any number of solutions. So then we go ahead and work out what the determinant is, and it can be expressed in terms of Wronskians of any possible pair of these solutions. So here we have the Wronskian of y2 and y3, taking the derivative of that. Wronskian of y1 and y3, y1 and y2. Now, the thing is, from Abel's theorem, the derivative of Wronskian is equal to minus p times the Wronskian. So that lets me, so I can replace each one of these, like W23 prime is equal to minus P W23. So now I have a common factor of P because I have a derivative in every term. So that gets factored out. And now I have this. But if I think of this as the cofactor expansion of the determinant of a 3x3 matrix, then I can discover that this expression in parentheses is a derivative of this matrix here, because you have y1 prime, y2 prime, y3 prime. I put them in the first row. And if I were to take the determinant of this matrix, I have y1 prime, and then this part here, y2, y3, y2 prime, y3 prime, that is a Wronskian of y2 and y3. And then I go to the next part of my cofactor expansion. I have minus y2 prime times the determinant of this matrix, y1, y3 prime, minus y3, y1 prime. That's a Wronskian of y1 and y3. And then I go to the last term of my cofactor expansion. I have y3 prime, determinant of this 2x2 matrix, y1, y2 prime, minus y2, y1 prime. That's a Wronskian of y1 and y2. So this is the determinant of this matrix. But look at this matrix. First row and the third row are the same. Anytime you have a matrix where any two rows or any two columns are identical, the determinant must be 0. So what this shows is that the Wronskian of any three solutions of this second order linear homogeneous ODE must be 0. So it's not possible, no matter what those solutions are, it's not possible for them to be linearly independent. So you have at most two because of second order. So if you want three linearly independent solutions, get a third order ODE. Any questions about how this unfolds? It might be difficult to see how this is equivalent to this. I definitely would not expect one to say, oh, that's clearly equal to this determinant. That's not an instant leap. The only reason one can see that this would even work is that looking at the indices. Here you have 1 and then 2 and 3, 2, 1 and 3, 3, 1 and 2. So because we have distinct indices in each term, that's what makes this going from this to this determinant even possible. All right. So back to the main dilemma. Like if you take the example from last time, Bessel's equation, use Frobenius' method to find one solution. It was also shown that when, at least in certain cases, if you try to use Frobenius' method to find the second solution, that would break down either division by 0. So we need another way, in cases like that, of finding a second solution. And this is one example of where that comes up. You are solving this equation on constant coefficients. Solve your characteristic equation, you end up getting a double root. So e to the lambda 1x is a solution, but e to the lambda 2x is the same, therefore not linearly independent. So how can we find a second solution? This will apply whether the coefficients p, q are constant or variable, doesn't matter. That's a nice thing about phonetic. What you do is you assume that your unknown second solution is equal to the solution you have, y1, times some function v. And it's always possible to write in that form because we have no idea what v could be. We're just trying to get an alternative equation using the fact that y1 is known to be a solution. So we go ahead and substitute our form of y2 into the ODE. So here we end up using product rule for second derivative, product rule for first derivative. And what I'm going to do now is rearrange these terms. I want to get all terms involving v together, and then v prime and v double prime. So here's the only term that involves v double prime. Here are all the terms that involve v prime, and all the terms that involve v. So you can factor out each derivative of v. But y1 is known to be a solution of the ODE. So this part right here in parentheses has to be 0. So now we have this. And that is huge because while this is still a second order equation for v, it's a first order equation in v prime. So because we were able to get rid of the term involving v, I can assign a variable v prime. I can call this w, and this is w prime. So then I can solve this equation for v prime. And the way to do that, here's the general solution formula. That's anytime you have a first order ODE like this, your solution, which in this case is v prime, is a constant times the exponential of minus this integrated. That's what I have here. Now this I can simplify to an extent, because if I look at this first term, I have integral of y1 prime over y1. If I make a U-substitution, actually I'm going to include that here. I'm also going to break this up into two integrals. Okay, so I've broken up this exponential in two. And then for this one, I'm going to take the constant factor of 2 and pull it out. And in this integral alone, I can make a U-substitution. How about u equal to y1? Then I have du is y1 prime x dx. So now this integral reduces to integral, whoops, that's du over u. There's no dx in it. Can't stop that. Don't be good. But this integral is evaluates a natural log of u, which is natural log of y1. Okay, and then I still want this separated. Okay. Then, from here to here, I use properties of logarithmic functions. This -2, I can move up here as an exponent. So now I have e to the log of y1 to the -2. The e and the log cancel, which gives me just 1 over y1 squared. If I still have the rest of this. Although it's constant times e to the integral of minus p, that's already known to be the Wronskian. So now I have this formula for v prime. Yeah, sure. And to get v, which helps me complete my second solution, I just have to integrate both sides of this equation. So, and then if I multiply by y1, that completes the definition of y2. So this right here is my formula for the second solution. So y1 times this integral. Now, here we have y1 outside the integral. Here, this one, y1 is inside the integral. So you cannot simplify with these. You gotta leave them alone. I can't get rid of this and say this is y1 first denominator. And any multiple of a solution of a homogeneous ODE is still a solution. So it doesn't really matter what the arbitrary constant is in this formula, just set it to 1. So this is the formula that you'll be using in the homework for this section in some of our problems to find a second solution. Now, as you know, when you evaluate an integral like this, normally you would add on a plus c. We don't care about the plus c in this case because if you think of this as you work out what this integral is, you add on a plus c, but that plus c is multiplied by y1. Well, that term, constant times y1, is already known to be a solution of your ODE. It's redundant, so we don't bother with the constant integration. So this method that I've shown you is called reduction of order because you have a solution already, y1. You use your knowledge of that solution to obtain an ODE of lower order. So you're working with a second order ODE, you're trying to find solutions to this. You end up being able to solve a first order ODE to obtain a formula for your second solution. Any questions about how this formula was arrived at? With Wronskian, just make sure that the solutions you get, y1 and y2, are linearly independent. Here we use the fact that y2 is equal to y1 times v. So then when you compute the Wronskian, v prime appears in here, other terms cancel, and we know what v prime is. It's 1 over y squared times the Wronskian. But you end up, but that Wronskian is equal to e to the minus the integral of p, which is non-zero. So that tells you that these solutions are linearly independent. They do form a fundamental set. So as an example of reduction of order, the variable coefficient problem, here's a Chebyshev equation. And we're going to focus on the case where n is equal to 0. So this term won't be here. So then, solution of the equation with this equaling 0, you use a constant function because you only have these derivatives of y. Where did light come from? It's really weird. Yeah, like this room is alive, but Okay. So y1 is equal to 1. That is a solution of ODE in the n equals 0 case. So now I'll use my reduction of order formula to get a second solution. So y2 is y1 integral e to the minus p over y1 squared. Well, y1 is 1, so that helps a great deal. Now, one thing to be careful about, to get the right formula for p of x, you have to get this ODE in a form where y double prime is by itself, and that's a coefficient of 1. So I have to divide by 1 minus x squared throughout. So my p of x is really minus x divided by this. So don't forget to do that. If you're going to use reduction of order, and your PDE is of a different form, isolate y double prime and turn by itself before you proceed, or you'll get thrown off. Now we have e to the minus integral of this. And if you use a U-Substitution, U equals 1 minus x squared, for which du equals minus 2x dx. Then you're able to evaluate the integral to get e to the minus 1/2 natural log 1 minus x squared. And using the same kind of simplifications that I did earlier, I can rewrite this as e to the natural log of 1 minus x squared raised to the minus 1/2 power. These properties of logs. The e and the log cancel out, so you get 1 minus x squared to the minus 1/2. But the integral of that is inverse sine. So that is your second solution. So y1 equals 1 and y2 equals inverse sine are two linearly independent solutions of Chebyshev's equation in the n equals 0 case. So let's find it, form a fundamental set. Questions about this example?
So we're not gonna put, let's see, on anything on the
In reduction of order, no. And just doesn't get you anything. Here's another ODE, variable coefficients, already written in the correct form. So y double prime is a coefficient of 1. And we have this parameter alpha. So one solution of this ODE is x to the 1 plus alpha over 2. So we're going to use reduction of order to find another solution, y2. So here we apply the formula. And okay, now what's interesting in this case, there's no y prime term in here. So this right here, that's q of x. There is no p of x, it's 0. Apologies if I accidentally said something contradicting that earlier. I just read that, but I looked at the video to see. All right, so no y prime term, there's no p, it's 0. So outside we have x to 1 plus alpha over 2. Down below we have this squared, so that's x to 1 plus alpha. In the numerator, we're just going to have e to the integral of 0. So we're just going to get 1 up top. So now we get x to the minus 1 minus alpha. So here too, in this integral, we can use any antiderivative of p of x. So again, there's no need to bother with a constant of integration here either. Because all that would do, if we did include that, it would lead to a multiplicative constant out front. Don't need that. So integrand becomes this. But for this, we can just use power rule. So then we get x to the 1 plus alpha over 2 times x to the minus alpha. So then we get x to the 1 minus alpha over 2. Now we have this constant factor of minus 1 over alpha. But again, we're just trying to find two linearly independent solutions. Any scalar multiple of the solution is also a solution. So there's no need to account for whatever constant factors. So we can just say y2 is the interesting part of this function of x, so x to the 1 minus alpha over 2. Then what you could do is take the Wronskian of x to the 1 plus alpha over 2 and x to the 1 minus alpha over 2 to confirm that these really are linearly independent. Questions about this one? Or now we've gotten to the end of notes, any homework problem? Whether it's the current or old homework, because there's still been a number of assignments not turned in yet. Nothing at all? Homework going swimmingly? Take a look at the schedule here. I have more material for this section. I'm looking at for my external site, the previous version of it. Oh, okay. Okay. I guess you could say that I goofed a little bit because I've forgotten that these notes that I just presented to you was meant to be spread out over 2 class periods. And I guess when I taught this 9 years ago, when I had to write everything on the board, it really did take 2 class periods to cover it all. And I accidentally covered it in 1. Sorry about that.
We were 10 minutes late in the beginning of class, so it kind of worked out.
Yeah.
We've been even earlier finished, so.
So my situation is, so here's the thing to ponder. Option number 1 is that in class on Tuesday, I forge ahead with whatever the next section would be, or it's the next section, which is chapter 8, that's meant to be started next Thursday. So I think what I'm going to do, I don't want to get ahead in the schedule, so I'm going to keep that next section for Thursday. What I'm going to do with Tuesday's class is I'm not going to cover anything new, but I want people, if choose. One is going to get homework time, because when I look at homework submitted so far, like the section I covered previously, 7.5, that corresponds to homework number 5. And I don't even have everybody's homework 1 yet. So I'm a little concerned about some individuals falling behind. Or at least I don't know where we're at until they turn something in. So what I will do is I will show up. And if anyone, whether in person or online, has homework questions, they can bring them. And or if you don't attend, to watch it later, maybe something that's brought up will help you. And if nobody shows up, then we don't have class. So, okay. Then I won't race through everything. And so let's good idea to pause and let people catch up. And who knows, I might just got myself a 3 hour, 15 minutes, but we'll see. That's up to you. I mean, I'm going to be here.
They would come anyway. That looks so well.
Yeah, I thought your teacher would like that.
Yeah.
So, yeah. It's less
Yeah.
than you expected.
Well, what's your tattoo? That's great.
Yeah. So. Okay, so